this video, I want to have a look at sketching curves that involve trig functions. So the example that we're going to have a look at asks us to sketch the curve y equals sine x plus cos x in the domain 0 to 2 pi. So the first thing we're going to do is we're going to find the value of the function at those endpoints. So to do that, we're going to say at x equals 0, then y is going to equal sine of 0 plus cos of 0. Now we know that sine of 0 is 0 and that cos of 0 is 1. So that's from looking at your basic graphs. So sine looks like this. So sine of 0 is 0 and cos looks like this instead. So cos of 0 is 1. So that's just going to give us 1. At the other end, we're going to look at x equals 2 pi. So y is going to equal sine of 2 pi plus cos of 2 pi. Now, because sine and cos both have a period of 2 pi, these values are going to be the same as these ones, but we can double check on our graph. So this is 2 pi here, so sine is 0, and 2 pi is here, so cos is 1. So we have 0 plus 1 equals 0. So from that, we have 2 points that our curve is going to pass through now. So we know its endpoints are 0, 1, and 2 pi 1. That's a 1 because 0 plus 1 is 1, not 0. All right, so there are endpoints. The next thing we can do is we can find our x-intercepts. So to find x-intercepts, we're going to set y equal to 0. So that means we're going to have 0 equals sine x plus cos x. So if we rearrange that, we can write it as sine x equals minus cos x, which doesn't look like it's helping us just yet. But if we divide both sides by cos x, we're going to have sine x over cos x equals minus 1. And sine x over cos x is actually tan x. So tan x equals minus 1, which means we can draw up our little diagram. So it's all stations to central. So tan is negative, so we're looking in this quadrant or this quadrant, and we need to find the size of our related angles. So from our special triangles, which are on your formula sheet, our related angle is going to be 45 degrees, which in radians is pi on 4. So that means our x that's going to make this true, well, this angle, if this here is pi on 4, then this angle round here would be 3 pi on 4, because we know that this line is pi, which is equivalent to 4 pi on 4. We know that this over here is 2 pi, and that's equivalent to 8 pi on 4. So that means that coming around to this line, so all the way around here, that would give us an angle of 7 pi on 4. So that means these are our two x-intercepts. Next, I want to find our stationary points. So to do that, I'm going to differentiate this. So we'd have y dash equals the derivative of sine x is cos x, and the derivative of cos x is minus sine x. So to find our stationary points, we're going to set this equal to 0. So we'd have 0 equals cos x minus sine x. If we rearrange that, we'd have sine x equals cos x. And if we divide through by cos x, we'd end up with tan x, because sine divided by cos is tan. So tan x equals 1. So using one of those diagrams again, all stations to central. Remember, we're only going between 0 and 2 pi as well. It's a positive 1, so it's going to be this one and this one. Our related angle is pi on 4, just like it was last time. Having trouble fitting that in there. But that means our x is going to be equal to pi on 4, or this one down here would be 5 pi on 4. So those are our x coordinates of our stationary points. Now we need to find the y coordinates and then determine their nature, so figure out whether they're maximums or minimums. So at x equals pi on 4, y is going to be equal to sine pi on 4 plus cos pi on 4. So we know from our special triangles, we know that pi on 4 is 45 degrees, and sine of 45 degrees is 1 on root 2, and cos of 45 degrees is 1 on root 2 as well. So that's going to give us 2 on root 2. But if we rationalize the denominator by multiplying top and bottom by root 2, I've run out of room, so I'm going to put it over here, we'd end up with 2 root 2 over 2, which just simplifies to the square root of 2. So that means we've got one stationary point at pi on 4 root 2. And we're going to figure out whether it's a maximum or a minimum in a minute. Then we need to do this same thing for 5 pi on 4. So we're going to have at x equals 5 pi on 4, then y would be equal to sine of 5 pi on 4 plus cos of 5 pi on 4. Now drawing ourselves a little diagram, we know that here is pi, so 5 pi on 4 is going to be down in this quadrant, and our related angle would be pi on 4. All stations to central means that both our sine and our cos are negative in this quadrant. So this is equivalent to minus sine of pi on 4, minus cos of pi on 4. And we've just figured out that pi on 4, sine and cos of pi on 4 are 1 on root 2. So we'll have minus 1 on root 2 minus 1 on root 2. So we're going to have minus 2 over root 2, which when we rationalize the denominator will just be minus root 2. So that means our second stationary point is going to be 5 pi on 4 minus root 2. So now we need to go through and figure out whether these stationary points are maximums or minimums. So you should be able to have a look at these and look at the y values and figure out that this one's looking like a maximum and this one's looking like a minimum, but we do need to confirm it. So to do that, I've drawn up my table of values. I've got my pi on 4 and my 5 pi on 4, and I need to pick values on either side. So I'm just going to pick 0, pi, and 2 pi because they're going to be really nice to substitute in. So we know that the gradient is 0 at these points. If we substitute 0 in here, we'd have sine of 0 plus cos of 0, which would give us 1. So that's positive. If we substitute pi in there, sine of pi is minus 1, sorry, 0, and cos of pi is minus 1. So that will give us minus 1. So we've got a negative gradient there. And 2 pi, if we substitute those in, that's just going to give us 1 as well. So that's positive. So that's just confirmed that our pi on 4 stationary point is a maximum, and our 5 pi on 4 is a minimum. So now we can use all of these features, all of these pieces of information that we found to sketch our function. Okay, so I'm going to put my endpoints in first. So at 0, I know that I've got a value of 1, so that's here. And at 2 pi, I know I've got a value of 1 as well, so that's going to be here. All right, our x-intercepts are 3 pi on 4 and 7 pi on 4. So 3 pi on 4 would be here. And 7 pi on 4 would be here. So this one here is equivalent to 6 pi on 4, and that's 8 pi on 4, so 7 pi on 4 is half in between. So we know our function passes through those 2 points as well. Now to do these ones, I'm going to approximate those as decimals. So pi on 4 we know is here. And root 2 is about 1.4 something. So that's going to be up here somewhere. So that's our pi on 4 root 2. And our 5 pi on 4 is going to be here. And we want ours to be minus root 2. So that's going to be down this direction somewhere. So that's 5 pi on 4 minus root 2. All right, and now we can join those up to form our curve. So doing that the best I can on this tablet thing. We can come down through here. That's a little bit wonky, but you get the general shape of that curve with all those key functions, all those key points. Let's have a look at what it actually looks like. If I use a program like GeoGebra, it looks like this. So that is the shape that we had, and it goes through all those values that we had as well. So that's having a look at how we can sketch curves that involve trig functions.